Let's jump into today's material. Today's material is mostly just going to be applications of stuff we've already talked about, not going to be a lot of new theory. Only one new major concept that we're going to have, the concept of concavity. And concavity is just basically second derivatives. So, not the fancy there. And a large part of what we're going to focus on today is graphing functions and getting familiar with what graphs of functions would look like based off of what the function is. Looking at the properties of the equation of the function and understanding its counterpart graphically. So for example, if a function has a positive derivative, what does that mean? What's our intuition for what the derivative of a function is?
It's the slope.
It's the slope. So if a function has a positive derivative at a point, it must have a positive slope. And so it's that type of understanding that we're going to connect. So first off, if, that's a prime up there, if f prime of x, so the derivative of f, is greater than 0 on some interval, I just stands for some open interval.
Wait, what does?
The big I there. I'm going to use I for just an interval. So if the derivative is positive on some interval, then we are going to say that f is an increasing function. And then similarly, if the derivative is down, then it's decreasing. I'll quickly do the proof of this one really quick, but most of the stuff is pretty straightforward. So, going to draw some arbitrary function really quick. There it is. What does it mean for a function to be increasing? It's going up the further to the right we go, right? I'm trying to make this one not so vertical.
You have to pick an interval.
Right, so let's pick some interval where this function is increasing. And we'll say it's going from, we'll pretend that that's the bottom, so we'll say it's increasing from here to here. We don't have to get the biggest interval, we could have done a smaller one, but it's increasing on that interval, right? What does it mean to be increasing? It means that if I pick any 2 points, call it x1 and x2, then the height of x2 is higher than the height of x1 if x2 was to the right of x1. That's what it means to be increasing. If I go over further, I'm up higher. And the more left I go, the lower I am. So, we'll scribble out this proof really quick. Proof, if the derivative of our function is greater than 0 on I, comma, then f is increasing. So I'm going to do that proof. I'm going to start out with grab 2 random points, x1 and x2. So let x1 and x2 in our open interval, whatever it is. I is this interval in our picture. Such that, which one's going to be bigger, x1 or x2?
X2.
x2. So such that x2 is bigger than x1. In other words, whichever of those 2 points are further right, let's call that one x2. Okay, what am I going to try and prove? I'm going to try and prove that f of x2 is greater than f of x1. That's what it means for a function to be increasing. If I grab 2 points, whichever one's further right better be higher up. That's what it means for a function to be increasing, right? So I am trying to prove, scratch that to the side, what am I trying to prove? I'm trying to prove f of x2 is greater than f of x1. Using the fact that the derivative is positive on this interval. You with me?
Yeah.
All right. Now, we remember the mean value theorem. What did the mean value theorem say? Scribble its picture just up here really quick. You got some function, pick 2 points, x1 and x2.
That the mean of them has to be somewhere on the one.
Perfect. So take the average slope between these 2 points. So the average slope will be like this line roughly, right? The mean value theorem says there has to be some point between them, call it C, such that the slope of C is exactly the same as that line.
Oh.
That was the mean value theorem.
Which one was the zero theorem where?
Intermediate value theorem.
Oh, I thought I was thinking that one.
Okay.
Okay, so.
We had the extreme value theorem, the mean value theorem, and the intermediate value theorem.
Yeah.
The extreme value theorem had to do with there being a top point and a bottom point, And then the intermediate value theorem had to be with if the function is continuous and I get this height and this height, then I have to be able to get every height in between.
Yeah.
If my function gets this high and this low, it must get every height in between those two heights. That was the intermediate value theorem. But we're talking about mean value theorem. So from the mean value theorem, I know that from mean value theorem, we know that there must exist C in I such that the derivative at C is equal to the slope between those 2 points. What is the slope between these 2 points?
It's
Rise over run, right? What's the rise from here? Let's try and quickly sketch this out.
it's f of x2 minus f of x1 over x2 minus x1.
Right. So this distance right here, it's the height of this point minus the height of this point. So this height is f of x2 minus f of x1. And then this distance, the run here, is just x2 minus x1. You guys me?
Yeah.
So rise over run is just f of x2 minus f of x1 all over x2 minus x1. Now what are we trying to prove? I scribble that to the side. Here's what we're trying to prove. I'm trying to prove f of x2 is greater than f of x1. What do I know about the derivative?
Positive.
It's positive. So I know whatever the derivative is at C, it must be a positive number because the derivative is greater than 0 on that interval.
Yeah.
I'm trying to prove that if the derivative is greater than 0 on that interval, then f must be an increasing function. Or in other words, f of x2 must be greater than f of x1. So 3, looking at this equation, just bring the x2 minus x1 to the other side. So then I'll write this numerator first. F of x2 minus f of x1 is equal to f prime of c times x2 minus x1. You follow what I did? I just moved this over here and then swap the order that I write the equation in. Good with the algebra?
Okay. Yeah.
Okay. Now, f prime of c is, what do we know about it?
Positive.
It's positive. x2 minus x1 is,
Positive.
how do I know that that's positive?
Because x2 is greater than
Because x2 is greater than x1. So I have f of x2 minus f of x1 is a positive number.
Which means that f of x1 has to be greater than f of x2.
F of x2 has to be greater than f of x1. Because when I took this number and I subtracted this number, I still had some left over.
Yep.
Right? So that gives me that f of x2 is greater than f of x1. Sorry, I did a lot of word explaining rather than writing it out, but I think you get the idea. Pretty straightforward idea. Pretty straightforward proof. And the proof for the second one, almost identical.
Right.
So, prove what your intuition already told you. If the derivative is positive, the function must be increasing. If the derivative is negative, the function must be decreasing. And if the derivative is 0,
It's at a, what's it called?
It's not possible.
Huh?
If the derivative is 0, then the function is constant, isn't it?
then the function is neither increasing nor decreasing at that point.
Yeah.
Not necessarily the function's a constant. Give you one example of a function that has the derivative 0 at a point would be a function like this. Comes up, levels out, and then just curves back up. So it's flat for just an instant right at 0. Would be a standard example of increasing, 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 0, increasing, increasing, increasing.
And if it's undefined, then it's also.
Yeah.
If it's undefined, then it's undefined. Oh, so that's what you're thinking about is our next topic. Reminder of what a critical point is.
Critical.
Which is 0.
So a critical point is where the derivative is 0 or the derivative is undefined. Both of those are what we call critical points. What's one of the reasons we were very interested in critical points? All our maxes and mins have to occur at critical points. And a huge application of calculus is finding maxes and mins. That shows up in all fields over and over and over again. It's a very common use case, finding where a function achieves a max or a min. So, very useful to be able to do that. Okay, so now a couple examples, just getting comfortable with this. So for 4.3, a bunch of your homework problems are going to say something along the lines of, find out where this function is increasing and decreasing, and find its all its local maxes, local mins, and absolute max, absolute min. That'll be a standard problem. So let's take this one and go through it. So let's look at our function f of x equals x cubed minus 12x minus 5. You can just rewrite here to remind us which one we're talking about. X cubed minus 12x minus 5. So this function has some picture. I have no clue what it looks like. One of the things we want to do is we want to figure out where the function is increasing or decreasing. Now, in order for a function to switch from increasing to decreasing, the derivative has to be 0 or undefined at some point that you cross. So that's going to happen at critical points. So the first thing we want to do is find the critical points of this function. How do you find a function's critical points? Take its derivative and see where its derivative is 0 or undefined. So f prime of x is equal to
3x minus 12
3x
squared
minus 12. Okay, there's our derivative. And so we want to know where that's equal to 0. Where is 3x squared minus 12 equal to 0?
2.
Move this to the other side. So we get 3x squared equals 12, divide both sides by 3, and I get x squared equals 4. Or in other words, x is equal to plus or minus 2.
Yeah, but why do you need the plus?
What?
What's 2 times 2?
4,
Times 3
12,
minus 12.
0,
What's negative 2 times negative 2?
4,
Times 3
12,
minus 12.
0.
So both 2 and negative 2 are solutions to that equation.
Okay.
There's 2 solutions. So we have 2 critical points at 2 and negative 2. So whatever this function looks like, I have no clue yet. Over here at negative 2 and over here at 2 are the only possible places where I could switch from decreasing to increasing or increasing to decreasing. So the question is, to the left of negative 2, is this function increasing or decreasing?
So you plug in negative 3.
Yeah, so plug in negative 3 really quick. We get a negative number minus, or sorry, we get, yeah, just really quick calculate it. 3 squared is 9 times 3 is, minus 12 is 15, a positive number. So the derivative is positive to the left of negative 2. So it's increasing over here. Between negative 2 and 2, what's it doing? Plug in 0, what do you get? Negative, so it must be decreasing between negative 2 and 2. And then plug in a number bigger than 2, what do you get?
Positive.
Positive again. So whatever this function looks like, it's increasing from negative infinity all the way to negative 2. Then it starts decreasing until it gets to 2. And then it starts increasing again after 2. You with me?
Yeah.
Okay.
Okay. So let's really quick, just to get a feel for what this looks like, let's find the height of the function at these points. So what is f at negative 2 equal to?
0.
F, not f prime.
Oh.
F. So we got negative 8 plus 24 is,
16.
minus 5 is
11.
11. So at f of negative 2 is 11. And then let's look at f at 2 and see what that is. Where did I get when I plug in 2? 8 minus 24 is, huh?
16.
Negative 16 minus 5 is
Negative 20.
minus 21. So now, very rough sketch. Not going to do very good. Here's negative 2. Here's 2. We'll call that 10, 20. We'll call that minus 10, minus 20. So my scales are different in the x and y axis, right? Okay. So f at negative 2 is 11. So here at negative 2, should put these numbers on this side. Here at negative 2, we're down here at negative 11. Somewhere like right there, right?
You're up, aren't you? Because it's positive.
Oh, positive 11. Thank you.
Then you have negative 21.
So here at negative 2, we're up at 11. And then here at 2, we're down to minus 21. So this function, what is it doing? It's increasing from negative infinity to negative 2. So whatever it's doing, it's coming up and it achieves a local max there. And then it starts going down. And it's going to go down all the way to this point and then shoot back up, whatever it does. It's going to look roughly like that.
Right now, she's done up.
Because it's increasing again after 2.
Oh, right. Okay.
So 2 here is a local min. It's at the bottom of some hill. Negative 2 here is at a local max. It's at the top of some hill. What's the absolute max of this function? Infinity. It gets arbitrarily large, so it doesn't have one. And what's its absolute min? It doesn't have one. So it just has a local max and a local min. And that's it. At each of those points. Good? Alright, let's do another example. One slightly more complex. So this time we are looking at x to the 1/3. We're looking at this one, right?
Yeah.
I'm just really quick going to multiply that out because I know we're taking a derivative and I don't want to have to do the product rule.
That's a good idea.
So x to the 1/3 times x is
X to the
X squared 1/3.
2/3.
when you
Actually,
multiply terms, you add exponents.
Oh, so
So it's x to the 1.
So
That's right.
x is the same as x to the 1. What is 1 plus a third? 4/3. So this is equal to x to the 4/3 minus 4x to the 1/3. Okay, multiply that to there, multiply that to there. Oh, you guys scare me.
So that's -3.
Oops. So
No.
x to the 4/3 minus 4x to the 1/3. Okay, now our derivative, so f prime of x, is then equal to
4/3
4/3
x to the 1
x 1/3
minus
minus 1/3.
4/3,
4/3.
because you got to bring down the 1/3 and multiply it by 4,
Yeah.
X to the -2/3.
Oh,
Negative
okay.
2/3.
Okay.
times x to the,
Negative 2/3.
I'm just going to put that down here. You okay with this? X to the 2/3 in the denominator?
Yeah.
You can't really tell that that's just 2/3, can you? We have minus 4 over 3x 2/3.
Are you gonna do the same thing with the other x? Or leave it out of the?
What?
Are you going? Oh my bad. No. Okay. Never mind.
Okay, because that one has a positive exponent.
Yeah. Okay. Right.
Okay, so now, our question, I want to give these things a common denominator. I'm going to multiply both of them by x to the, I'm going to multiply this top and bottom by x to the 2/3. Okay. You with me? So I'm multiplying it by 1, but top and bottom by x to the 2/3. So that's going to give me 4x over 3x to the 2/3 minus 4 over 3x to the 2/3. Did you follow my algebra there? Just multiply this one top and bottom by x to the 2/3. And since now they have the same denominator, which was the whole point, it's 4x minus 4, or factor out the 4. It's 4 times x minus 1 all over 3x to the 2/3. Okay, that's way easier to reason about. Because we care about when it's 0 and when it's undefined.
Oh, yeah.
And when is it 0? Whenever the numerator is 0. And when is it undefined? Whenever the denominator is 0, or we end up taking a square root of a negative number. But there's no square roots here, so we don't have to worry about that. Right? So what are our critical points?
1
1. That's what makes the whole term 0.
and 0.
And 0.
And then 0 is where it's undefined.
Yeah.
Because I can't divide by 0, and if I plug in 1 in the numerator, we get 0.
Yep.
Okay, so there's our two critical points. So whatever this thing looks like, 0 and 1 are its critical points. And in order for a function to switch from increasing to decreasing or decreasing to increasing, it has to go through a critical point.
Yep.
So these are the only places where it could possibly switch from increasing to decreasing. Now we just need to test each of these intervals and see whether or not it's increasing or decreasing on that interval. Right? Okay, so let's look to the left of 0. Is our function increasing or decreasing? If I plug in something like -1. Let's see. The denominator, we're squaring in the denominator, so the denominator is going to be positive. Our numerator, we get -1 minus 1 is -2 times the positive is still negative. So it's decreasing. You see that? Okay, let's plug in a number between 0 and 1, like 1/2. The denominator, since x is being squared,
Decreasing.
is always positive. So we don't need to worry about the denominator. And we just look at the numerator to determine the sign. So plug in 1/2. 1/2 minus 1 is
-1/2.
a negative, times a positive is still negative, so it's still decreasing. So just because you have a critical point doesn't mean that your function has to switch from increasing to decreasing. It's just it can't switch from increasing to decreasing unless it goes through a critical point. And then finally, look to the right of 1, so plug in something like 2, and what do we get?
A positive.
Positive. Okay, so now let's get a rough idea of what this function might look like. So let's look at the height of the function now at each of those points. What is the height of the function at 0?
0.
0. And what is the height of the function at 1?
4/3.
What's 1 to the power of 4/3?
4/3.
What's 1 to the power of 4? What's 1 times 1 times 1 times 1?
Oh.
1. Now take its cubed root.
1.
1. That was some crazy good algebra. Okay. So 1 minus 4 is -3. Okay. Now, let's roughly sketch out what this equal would look like, very roughly. Don't read too much into my pictures. I'm sure the author has pictures of what these all look like if you want to look in the book as we go. Make sure I'm not way out of whack. But so our function is 0 at 0.
-3 at 1.
But 0 is where our derivative was undefined. So that means it's going to be vertical at 0. So whatever this function is, let's see, it's decreasing until we get to 0. So I'm not sure what it looks like, but something like, it's going to have to be tangent there, and then level out, let's see, at 1 we're at -3. So then it's going to have to do something like this, and then shoot back up. So our function is going to look roughly like that. Decreasing, decreasing, decreasing. Right at 0, we're straight up and down, so our derivative is undefined. It has an infinite slope, so to speak. And then we taper off, and here's where our derivative was 0, and then we start increasing again.
Is the function defined?
Why can't you move that down?
The function is defined at 0.
Oh.
The derivative wasn't defined at 0.
Right.
Two very different things. Just
Why
because
is
you're...
that,
Go ahead.
up first? Why can't you move it decreasing in the negative?
So my function had to be decreasing
Yeah, but why can't you move it down into
Because
the third
the
quadrant?
function at that
because the height is 0 here. So my function has to be decreasing all the way down to 0. So everything to the left has to be bigger than 0 because my function's been constantly decreasing.
Okay,
It can never go up.
that makes sense.
So this function's been decreasing from infinity all the way down to 0 right here. Keeps going down, and there's where it finally starts increasing. Make sense? Okay. One more of these before we move on to the next section. So f of x this time we're looking at sine squared of x minus sine of x minus 1. All right, derivative. Impress me.
Cosine?
2 cosine.
Remember that sine squared of x is sine of x squared.
Right.
What?
Sine squared of x is sine of
So
x.
it's going to be 2 subtract cosine to the power.
So it's going to be 2. So chain rule. Let's think for a second. Imagine I had u squared. What's the derivative of u with respect to x?
2u.
2u times du dx, whatever that is. Right?
Yeah.
This time, we have a sine of x. So it's going to be 2
Sine of x.
times whatever that was inside of there, times the derivative of sine of x with respect to x, which is
-1 cosine.
just cosine of x.
Cosine. Sorry.
Derivative of sine is just cosine. Okay, so that's that piece. So we have 2 sine of x, cosine of x,
Okay.
minus, what's the derivative of sine of x?
Cosine of x.
Cosine of x. And the derivative of -1 is 0. So we're good. Okay. So there is our function, or the derivative of our function. So what is, oh, and it was on the interval. I think it was supposed to be on 0 to 2 pi most likely. Otherwise we have infinitely many critical points. So I'm guessing it said something like that. Yes, on the interval 0 to 2 pi. Okay. So we're looking from 0 to 2 pi. What are our critical points? Where is our derivative 0?
0.
Well, it's still kind of hard to reason about this. Normally, you want to get it as, you want to factor it so it's a product of two things. Then whenever one product is 0 or the other one is, that's where your zeros are.
Oh, you already have that.
No, that's a difference. I want it as a product. So I'm going to factor out the cosine of x.
I know, but if x is 0, it doesn't matter, it's 0.
No. No.
Yeah, but I'm trying to figure out where it's 0.
Okay.
When is this equal to 0? What value of x makes this 0? That's hard to reason about.
X is 0.
X is 0 is one value. Actually, no, you're still wrong. Because when x is 0, that makes this term go to 0, but we get a negative 1 there. So no, 0 does not make it go to 0.
Okay, yeah.
So we want to figure out what values make this 0. Well, that's the same as what values make this 0. And now this is 0 whenever this term is 0 or when this term is 0.
Yep.
So when is cosine of x 0?
Hold on, is it when sine of x is 0?
No.
Okay.
Cosine.
It's when sine of x is 1/2.
Cosine.
Because we want 2 times 1/2 minus 1 will be 0. So, sorry, when I say this term, I meant this. We want to know where that is 0 or where this thing is 0. When you're multiplying two things together, if either of them are 0, the entire product is 0.
Cosine is 0.
So when is cosine of x 0?
Uh,
On your unit circle, when is your x coordinate 0?
0.
Or half pi and
Your x coordinate 0 right there? Or your y coordinate 0 right there?
Oh, yeah. Yeah, but it's.
Where is your x coordinate 0?
At 2 pi. Right.
At the top of the circle and at the bottom of the circle.
pi half.
That's where your x coordinate is 0.
Yeah, that's right.
These are where your y coordinates are 0.
Well, I wasn't referring to that. I was referring to up and down, but I meant at 0 of the line.
And
Well, we talk in terms of angles. What angle is it 0 at?
90 and 270.
90 and 270, or to use same language, at pi halves and at 3 pi halves.
Oh, that's what you wanted. Okay.
Yes, that is exactly what I wanted.
I was trying to figure.
Now,
Are we on?
we also need to know where this thing is equal to 0. So I want to know where 2 times sine of x minus 1 equals 0. Or in other words, where 2 sine of x is equal to 1. Or in other words, where sine of x is equal to 1/2. So where is the height 1/2? What angles give me a height of 1/2? So 1/2 will be roughly right there. So what angle gives me that height and what angle gives me that height?
Root 2 over 2.
What angle?
45.
No, 45 gives me root 2 over 2. We want the angle that gives me a height of 1/2.
Oh, so root 3 over 2.
root 3
That
over
gives you 1/2. I'm confused. I don't know.
What's the angle? Our angle is going to be
60.
radians. That's not going to be 60 degrees, it's going to be
45.
Pi over 6.
30 degrees or pi 6.
How is 30 degrees high? That doesn't make sense.
Do we need a,
Hey, it's been a while. Right?
oh my goodness. I'm going to have to give you guys a unit circle on your midterm as well, huh?
Maybe.
Yeah.
All right.
Doesn't make sense. Your question just doesn't.
My question is, where is the sine equal to 1/2? So let's orient the scene correctly. Where's the top? There we go.
Your question was when does it reach 1/2?
When is the sine 1/2?
So
When
why-
is the height of your coordinate
Your-
1/2?
Your picture threw me off because I thought you meant 1/2 on the unit circle, which would be 45 degrees.
Oh. That's not.
You're
so
picking some weird 1/2.
It's still. It's
When is the height 1/2?
30 degrees.
At 30 degrees or
That's
pi 6. And where else is the height 1/2?
I don't know, 150 degrees. of
150 or 5 pi 6. Okay. So get that out of here. Now that you saw it and memorized the whole thing, and
Yeah.
we don't need it anymore.
Yeah.
So a pi 6 and 5 pi 6. So those are our critical points. And then we can determine if the function is increasing or decreasing on each of these intervals. So let's quickly write these out in order. So pi 6. Next is going to come pi halves. Next is going to come 5 pi 6. And then next is going to come 3 pi halves, right?
Yep.
And so now we just need to figure out on what intervals this function is increasing or decreasing. So to the left of pi 6, and I guess it goes all the way back to 0 and all the way over to 2 pi. That's our whole interval, right?
Yep.
So between 0 and pi 6, is our function increasing or decreasing?
Increasing.
looking at this.
Let's see.
So, let's really quick scribble a circle right here to help us think. So if we're looking at a point between 0 and pi 6, so say that pi 6 is roughly like this.
Yep.
So then we're looking at a point like right over there.
Positive.
Well, is the cosine positive or negative?
Positive.
Positive. Okay. Is the sine of x more or less than 1/2?
Less.
Is the height of that
Less.
point more or less than 1/2? It's less. So this is less than 1/2. So 2 times something smaller than 1/2 is smaller than 1.
It's still positive.
Smaller than 1 minus 1 is
A negative number.
negative. So negative, positive is negative. This function would be decreasing from 0 to pi 6.
Gotcha.
Now let's look between pi 6 and pi halves. So here's pi halves. So we're looking at a point roughly right there. Okay. Once again, cosine is
Positive.
Positive.
positive. And the height is more than 1/2.
Yes.
So
Okay.
2 times the height is going to be more than 1.
Positive.
So positive, positive. So our function's increasing on that interval. Okay, between pi halves and pi 6.
The rest of it's negative all the way straight.
5 pi 6 over here. Oh, here's 5 pi 6. So we're talking about a point roughly right there.
It's negative.
So looking at that point, cosine is going to be
Negative.
negative. The height is more than 1/2. 2 times more than 1/2, more than 1. So positive, negative times positive is
Negative.
negative. Now let's look between 5 pi 6 and 3 pi halves. 3 pi halves is straight down. So now we got a point like right there.
Positive.
It's negative. Yeah, positive.
Cosine is going to be
Negative.
negative. The height is going to be more or less than 1/2.
Less.
Less.
Less. So this is going to be negative. So negative times negative is
Positive.
positive. And then finally between 3 pi halves and 2 pi, so now our point is somewhere like right there. The cosine is
Positive.
positive, and the height is more or less than 1/2.
Negative. So
Less, so it's going to be negative, and so decreasing. And now I won't bother drawing out what this function looks like, but it's going to have decreasing to go into increasing. It's going to have a local min here, local max here, local min here, local max here.
So
Potential min, local min, or local max at the ends, depending on how it goes. Local max here, and local min here, because it was going down at the start. Okay. How your answer should be given, sorry. Your homework problem is going to ask you something along the lines of, on what intervals is this function increasing? So the actual answer will look something like increasing, and we are increasing on which intervals? We're increasing on the interval
Pi 6.
what do you
pi
got?
6 to pi halves. Here's what your actual answer would
Yeah,
look like.
I'm saying the same thing.
5 pi 6
to 3 pi half.
to 3 pi halves. And then you would say it's decreasing on interval 0 to pi 6, pi halves, 5 pi 6, and then 3 pi halves, 2 pi. So that's what your actual answer would look like. That's what the problem was actually asking us to do. Find the intervals where it was increasing or decreasing. That's what we were supposed to do for all these. I was just trying to connect it with the graph.
That makes sense.
Okay. So now that finishes that section. Okay, so the next section is all about concavity. Concavity is given to us by the second derivative of a function. The first derivative tells me the slope of the function.
Okay.
Slope is change in height. If I have a positive slope, that means my height is going up. If I have a negative slope, that means my height is going down. Concavity is my change in slope. Is my slope getting steeper or is it getting shallower?
So it doesn't matter positive or negative.
Well, let me show you positive concavity. Here is a positive concavity curve. The slope is constantly getting more steep. If you were to walk this path, it's constantly getting harder and harder for you to walk it. Right? Here the slope is really negative, and then less negative, less negative, less negative, less negative, 0. More positive, more positive, more positive, more positive, more positive. Here's a curve that is completely negative concavity. A concave down curve, we call it. if you were to walk this path, it's constantly getting easier the further you go. The slope keeps on decreasing,
Which, yeah.
right?
Yeah.
This one is hard at the beginning, real easy at the end, if you had to watch that. This one is really easy at the beginning, hard at the end. The slope here keeps increasing, the slope here keeps decreasing. Make sense? Okay. So that is concavity. If the concavity is increasing on some interval, we say the function is concave up on that interval. If it's decreasing on that interval, we say it's concave down on that interval. Concave up will have some resemblance of this shape to it. Concave down will have some resemblance of this shape to it. One of the ways people remember which one's concave up and which one's concave down is smiley face versus frowning face. If you're filling up, you're smiling. If you're filling down, you're frowning. Concave up, the smiley face. Concave down, the frowning face.
Yeah, it's pretty sure.
Common mnemonic. Okay. So, a function's concave up if the derivative is increasing. A function's concave down if the derivative is decreasing
Isn't it-
on some interval.
Isn't it the double derivative?
No.
No.
This function is concave up because the slope is increasing. The derivative is increasing.
Yeah, but why
Not
would
the
you say
double,
the
not the
derivative?
double derivative decreasing, right?
The double derivative, f double prime, tells me the change. This gives me the change in f prime. Just like f prime, this gives me the change in f. If I have a positive derivative, that means the height of my function is changing. If I have positive concavity, that means the slope of my function is changing.
Yeah, that makes sense.
Good. Yeah, easy to get mixed up. Which is talk about which. That was strange.
Physics.
Not sure how to talk like that. Okay. So, this, not going to bother with this proof, but doing the proof of this is a lot like doing the proof up there. The proof is that if the double derivative is greater than 0 on some interval, then the derivative is increasing, or in other words, the function's concave up. And similarly, if the double derivative is less than 0 on some interval, then your function is concave down. The proofs for this, almost the same as the proofs for that. Okay. Now we have a notion of an inflection point. An inflection point is kind of like to a double derivative what a critical point is like to a derivative. Kind of.
Oh, I see.
So what is an inflection point? An inflection point is going to be where the concavity changes signs, goes from being concave up to concave down or concave down to concave up. But we only have an inflection point if we only have an inflection point at a point if that point has a tangent line. Why do we say has a tangent? Let me give you an example of switching from concave down to concave up. Here's a function switching from concave down to concave up. So here it's concave down, and here it's concave up. My inflection point somewhere like right there, I don't know. I didn't draw that quite how I want to. Let me try one more time. I want it to be vertical right there. So let me try it one more time. Coming up, trying to get a vertical line as we switch. So that's a little bit closer to vertical. So this is a critical point. It's where we switch from concave down to concave up. And we require that a tangent exists at that point in order for it to be a critical point. Why don't we say just the derivative exists there? The reason we require a tangent line rather than saying the derivative exists there is because the tangent line can be vertical.
Oh.
And at that point, the derivative doesn't exist.
So I just have tangent lines, but not necessarily.
Not necessarily a derivative, but a tangent line. And a tangent line is almost the same thing as it has to have a derivative.
Yeah.
It's just including this case where the derivative was undefined because it's vertical. So we just want to make sure we capture that case. And so that's why it's worded just a little weird.
If that makes sense.
And because we wouldn't, because imagine the function were discontinuous at that point,
Then it break.
then it would break. And so We don't want to include those types of cases. Okay, so that's what an inflection point is, where it changes from positive concavity to negative concavity or vice versa, and the tangent has to be able to exist at that point. So if the derivative exists at that point, for sure a tangent does. But it's possible the derivative doesn't exist at that point, and we could still get a tangent if we want to. Another thing you'll notice is, at an inflection point, the tangent will intersect the function. So look at, one more time, let's look at the one I had there. Well, now it doesn't matter. So here is our inflection point, somewhere like right there, right? Now look at the tangent line at this point. If I do the tangent line at this point, it looks roughly like this.
Yeah.
Notice that it stays on the same side of the function, close to that point. Maybe way out here, this thing shoots up and it intersects clear out there. We don't care about that. But close to that point, it doesn't intersect the line, it just touches it and goes away. At an inflection point, your tangent line will always intersect the function at that point. And will cross from one side to the next. That will be another property that these inflection points always have.
Is there a proof for that? Why is there proof for that?
You can come up with a proof for it, but it's more a way to quickly pictorially identify a point, like a quick sanity check for you. Because you have pretty good intuition for where that would happen. A huge part of what we're after today is being able to look at a graphical representation of a function and get a lot of insight to what that function actually is. Or to be able to look at a function written out and get a sense for what its graph must be like. And being able to go back and forth in that kind of intuition.
Why can't you do that tangent like where they switch? Why can't you draw it like a normal one?
Because that's not tangent line.
I thought tangent lines can't cross each other.
In general, they can't. So the tangent line is the line that goes through that point and has a slope equal to the derivative at that point. And if you calculate the derivative at that point and drew the line with that slope,
oh, then it would break like that.
tangent lines were giving us intuition for derivatives give us slope at a line.
Okay. Makes sense.
But yeah, since the curvature there switches, there's no way for you to draw a line going through that point that doesn't cross from one side to the other unless you drew, right? Yeah. Okay. So there's concave up, concave down, inflection points. And now, in finding a local max and a local min, so far the way that we found a local max or a local min is first we found a critical point, right? And so let's say I have this critical point at 0 on some function. I look to the left and it's decreasing. I look to the right and it's increasing. So then at 0 we must have had a local max. Right? And the way we determined that is we had to look at a point to the left and we had to look at a point to the right.
Local min, wouldn't it be?
Oh, local min, thank you. We are decreasing and then increasing. So local min, how do we determine it's a local min? We have to look at a point to the left and the right. And how do we determine if it's a local max? We have to look at a point to the left or the right. Instead now, what we're going to do is just look at the derivative at that point and then the second derivative at that point. If the second derivative is positive, then it's concave up. And so it must be a local min. Conversely, we check the second derivative at that point. If it's negative, then it must be concave down, and so we must be looking at a local max.
Or an inflection point.
So pick the inflection point, look at its second derivative at that point. If it gives you a positive number, it's for sure a local max, or a local min. If it gives you a negative number, it's for sure a local max.
So
And if it gives you 0, you can't decide, and it could be one or the other.
if you already have the function, why can't you just graph it? I mean, how are you determining where to put these?
So, I give you, for one, here's just one quick check for what you're talking about. I give you some graph like this, whatever, and I tell you that this was x5 thirds minus 3x squared plus 7, whatever it was.
Yeah.
And I say, I want to know exactly where that bottom is. And you see the tick mark on your calculator, here's 6, here's 7. Where exactly is the bottom of that function? We are very interested in applied mathematics in finding precisely where those maxes and mins occur. In physics, they're called stationary points. They're points where states are stable. And we want to know exactly what that is. Having some picture doesn't just magically tell you that. You can zoom in on your calculator and zoom in and zoom in. And waste your life zooming in trying to get a good approximation. Or you can quickly calculate where exactly it is.
So how do concaves help with that?
Concavity.
Or concavity. How does that
So really quick, you find your critical point. You find out that's a critical point. Now look at the second derivative there. And you know that, oh, it must be a local min since we were concave up. And you don't have to bother drawing out the function and figuring out what the function looks like.
Oh, I was going to say, why can't you just look at it?
Right, so we could go through the pains of drawing this out. Then we could calculate the derivative of that thing to figure out where that min is. And then we can tell based off of the picture, okay, it must be a min. Maybe, for all we know, the scale of our calculator is garbage. And if we would have zoomed in, it would have actually been something, who knows? And you would have accidentally picked one of these points. That way zoomed in,
Yeah. What?
it could be just a scaling issue. You cannot read too much into pictures. You're used to functions that behave so nicely that you can infer a lot from the picture. But maybe you had some atrocious function where from a distance it looks nice and smooth, but when you zoom in, you see it's actually bumpy. And where that derivative was 0 when we zoomed in was actually a local max and not a local min.
How do you determine that? That's so weird.
Well, you determine it by looking at the function and then taking its derivative, finding the critical points, and you can either test a point to the left or the right of it in between two critical points and see if it's positive, increasing or decreasing, or you can take the second derivative there and see if it's concave up or concave down. But we'll do a bunch of examples.
Okay, that'll help.
But so in general, here's how we do it. If your derivative is 0 at a point, first off, these inflection points will always occur at points where your second derivative is 0 or undefined. Okay? Now, just because your second derivative is 0 or your second derivative is undefined does not mean it's an inflection point. But if it's an inflection point, it has to be one of those two things. So your inflection points, your inflection points would have to occur where those happen.
Okay, same thing as the last one.
Very similar to the last one. With the last one, our local maxes and local mins had to occur at critical points. So if you're looking for a local max or a local min, it had to be at a critical point. If you're looking for an inflection point, it has to be, we don't have a name for it, but where the second derivative is 0 or undefined.
Isn't that just a critical point?
No, critical points are first derivative, being 0 or undefined. These are where the second derivative is 0 or undefined.
Okay.
Completely different points.
So the derivative of a critical point.
Yeah, the derivative of a critical point isn't necessarily undefined.
Okay, that makes sense. So there's no word for it. But
We don't have a special name for those points. Okay, so if your derivative is 0 and your second derivative is positive, so we're concave up and we're at a point where the derivative is 0, the slope is 0, then you are for sure at a min, a local min or an absolute min, but for sure a local min. On the other hand, if your derivative is 0 and the second derivative is negative, so it's concave down, you're at a point where it's concave down on the function, and at that exact point your derivative is 0, you must be at a max. On the other hand, if your derivative is 0 and your second derivative is 0, you can't conclude anything. It could be a min, it could be a max, it could be neither. And so you can't conclude anything in that case. And we will see examples of each of these.
okay.
All right, so let's start turning through the examples. So our first example, we're looking at y equals x cubed. Here's our function. We're picking one intentionally that we already know what it looks like, right? So the cubic function looks something like this. Something like that, right? Okay, so first off, let's look at its first derivative. What's the derivative of this, y prime?
3x squared.
3x squared. Where is 3x squared negative?
Nowhere.
Nowhere, it's always positive. In other words, this is telling us our function is always increasing or 0.
Oh, second.
To the right.
So this function is always increasing or it's 0.
Right.
Where is our derivative 0?
What x?
At 0.
Yeah.
So notice that if we also called that f of x, just like we can write it, notice that f prime at 0 is equal to 0.
Yep.
Right? Now let's look at y double prime. what's that equal to?
6x.
Wait, what? Oh, sorry. Yeah.
6x.
6x. When is 6x negative?
When x is negative.
For any negative x. So that means everywhere to the left, this function is concave down. And notice that it's part of a frowny face. All the curvature from here to here can be found on some frowny face that we draw.
So that means the slope is decreasing along that line?
So that means that the slope is decreasing. The slope keeps on becoming more and more shallow, clear until it gets to 0.
Okay.
Now if we plug in a positive number to the second derivative, it's positive. So it's concave up over here. Its curvature can be found on a smiley face. And on that whole interval, now the slope is increasing again. But notice that our second derivative, f double prime at 0, is equal to what?
6x what?
6x.
Oh, if you plug in 0.
If you plug in 0, what do you get?
0.
0. So our first derivative was 0 and our second derivative was 0. In that case, you cannot conclude that's a max or a min because it might not be. So this was giving you an example of where your first derivative was 0, your second derivative was 0, and it was neither a min nor a max. You with me?
Yeah.
Okay. Let's see everything that we were supposed to do on this. We were supposed to find out where it's increasing, where it's decreasing. We talked about that. Where it's concave up and concave down. This thing is concave down on what interval? Just write these out really quick. Where is it increasing?
It's increasing.
It's increasing everywhere.
Yeah.
From negative infinity to infinity, it's always increasing. Where is it decreasing? Nowhere. Where is it concave up?
Negative infinity to 0.
From 0 to negative infinity.
To infinity.
0 to infinity, thank you. And then it's concave down
From negative.
from negative infinity to 0. Because you go left, right. Okay, so that's writing out that information if you were given, it was given to you on the problem. And we were supposed to find,
A rough graph.
Graph.
oh, and the rough graph we already got.
Yep.
Okay? Our next example, y equals x squared. Picking ones that you already know the graph intimately so that you can see how all this relates to the graph. And rather than writing it as y, I'm going to write it as f of x. So we can plug stuff in. So f of x equals x squared, right? What does this look like? It looks very roughly, that was terrible.
Extremely roughly.
Extremely roughly like that.
Yep.
Some parabola. Stretch out a little bit, but who cares? That's just changing scale. Right?
Yeah.
Okay. So first off, let's look at our derivative. What's f prime of x?
2x.
2x. Where is 2x positive? So where is our function increasing?
Positives and negatives with negatives.
It's increasing everywhere from 0 to infinity. It has a positive slope. Where is it decreasing?
From negative infinity to 0.
From negative infinity to 0. Now let's look at its concavity. So let's look at f double prime of x. What does that equal?
2.
2. Where is 2 negative?
Nowhere.
Nowhere. And so the whole thing has positive concavity. It's entirely concave up. So where is it concave down?
Nowhere.
It's not. Where is it concave up?
In the
Everywhere.
infinity.
It's going down on the other side.
Concavity. Concavity isn't where it's decreasing. Where is it concave down? That's where the slope is getting smaller. The slope here is always getting more and more
that's
positive.
fine. Okay, yeah, I got it.
Yep, you're gonna get those wires crossed a bunch and have to refix them in your head a bunch.
That's right.
Okay.
Y equals 3 plus sine of x.
Let's look at another one. This time, well, we do know what this picture looks like, but we'll draw out the picture really quick. So we're looking at y equals 3 plus sine of x, or sine of x plus 3, from 0 to pi. So what is that going to look like? Here's 0, here's 2 pi, here's pi, pi halves. We won't bother writing in numbers for those anymore, and then break up into quarters. Okay, so 1, 2, 3, 4. It's just a sine function shifted up 3, right?
Yeah.
Sine at 0 is,
1.
0.
sine at 0 is 0 plus 3, he shifts it up here.
Oh, right. Sorry.
Sine at pi halves is 1 plus 3 is 4, right?
Yeah.
And so it's going to, I didn't draw it very accurately, but we know that it looks something like that. Okay, but let's see how we could have gotten that information from this, like we should have been doing. So we're looking at f of x equals sine of x plus 3, right?
Yeah.
So first off, what is our derivative?
Cosine of x.
Cosine of x. And what is our second derivative?
Negative sine of x.
Negative sine of x. Good. Where is cosine of x positive?
Between.
Well, let's really quick find our critical points, I guess. Where is it 0? Where is cosine 0?
At
Pi halves and then 3
And-
pi
and
So our critical points we have at pi halves
and 3 pi halves.
2 halves.
and 3 pi halves. Right? Now, let's look at the concavity at each of those points. What's sine of pi halves?
Pi
1.
halves.
Sorry.
Negative 1.
So the whole thing is negative 1.
Yeah.
So the whole thing is negative 1. So at pi halves is a local min, or a local max, because it's concave down.
Yeah.
So I know that here at pi halves, we have a local max, and it's concave down, so in between, it has to look like a brownie face.
Okay.
Right?
Yes.
And 3 pi halves, when we plug that in, sine of 3 pi halves is negative 1, make it negative is positive, so it's concave up there. So over here at 3 pi halves, we have
Smiley face.
positive concavity. Right?
Yeah.
And obviously, we knew that that's what the sine function looked like if we shifted up 3 units, but see how we're getting it from this information. And its inflection point, where it switches, is going to be where this is equal to 0. And where is sine of x equal to 0? At 0, at 2 pi, but at pi. So our inflection point is right there. So we should have found our inflection point first so that we know where it stops being concave down and where it starts being concave up. And the switch is right there.
Yeah.
Okay. Ones that we don't have as much intuition for. Let's now look at f of x equals x to the 5/3.
Okay.
It's a parabola divided by the cube root. Right. Or not a parabola, it's a cube root divided by the cube root.
Okay, it's that.
How do you
Let's
know?
mess with this.
Okay.
So what's the derivative here?
It's
5 thirds.
X.
X to the power of 2 thirds.
X to the 2/3 like that, right? And then finally, what's f double prime?
Oh boy.
10
7.
over 9. 10 nines. X to the power of 1/3. Negative 1/3.
So 10 ninths times x to the,
1/3.
Negative 1.
Negative 1/3.
yeah, I'll do it in 2 steps.
And then 10 over 9x.
You okay with that?
Yeah.
Okay. So, let's find our critical points. Where is this equal to 0, or where is it undefined?
0.
0.
0. So that's our only critical point. Let's check the second derivative at that point. The second derivative at that point, what do I get when I plug in 0?
0.
Undefined.
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 Oh, yeah.
Right?
Yeah.
So,
Right.
this isn't necessarily a local max or a local min. Let's test a point to the left really quick, see if it's increasing or decreasing. If I plug in a negative number, what do I get?
Negative.
Negative.
Negative squared is positive. Do whatever you want after that. It's going to be positive.
Times the.
And it's going to be positive over here. So this function is always increasing, right? And our derivative at 0 is 0.
Yeah.
Weird.
Let's check. This next one is going to be for its concavity. So our concavity was undefined at 0. Let's look to the left. If we plug in a negative number, what do we get?
Negative.
Negative. So it's concave down over here. Over here, if we plug in a positive number, what do we get?
Positive.
Positive. So 0 is going to be an inflection point. It's a point where we switch Inflection points always either happen where the second derivative is 0 or undefined. The second derivative is undefined at 0. So it could be an inflection point.
Could be, but it's not.
And we just confirmed that it is. The concavity switches there.
So what's with the upper one?
So I know this thing. So this was the slope, just remind us. And this was concavity.
Oh, okay.
So drawing them both out. They happen to align. That didn't have to happen. So now, sketching out this function, let's get a feel for it. Whatever this thing is doing, 0 here is going to be our point. It's concave down going to 0, right?
Mm-hmm.
What does concave down look like?
That's frown.
Frown.
So it's increasing but concave down. So it's a frown. It's part of a frown, but increasing. So it's an increasing half of a frown.
Like a cubic.
Yeah, so it's going to come up like this. Up to 0,
Okay.
right?
Mm-hmm.
And now, to the right of it, it's still increasing, but now it's concave up. So it's smiley face, and it's a half of a smiley face that's increasing. So,
Looks like cubed.
and it looks a lot like a cubic.
Yeah, that makes sense.
Good?
Can we take a look at the absolute value function?
Take a look at the absolute value function.
Yeah, can we use that as one of our examples?
There's no point because the concavity is 0. Because the slope doesn't change. It's a piecewise function. And so on the right hand side, the slope is positive 1. And so the concavity is 0. The slope doesn't change. And on the left hand side, the slope doesn't change. So looking at lines or linear functions are very boring in terms of their concavity. Because linear functions have 0 concavity. The slope stays the same. Okay. Next one. X to the 4. Let's get a sense for what this thing must look like. Although we probably already know in our heads. X to the 4. What's our derivative?
4x to the power 3.
4x cubed. What's our second derivative?
12x squared.
12x squared. Okay. For our critical points,
0.
we have 0. And that's it. And we're increasing over here. We're decreasing over here.
Wait.
For
Okay.
prime of x.
Right. Okay.
Okay. Now for our concavity, where's the 0?
24. 0.
0. And it's positive to the left and positive to the right. So our whole function is concave up. It's decreasing
How's it?
as we approach 0, and it's increasing
Oh.
as we leave 0.
Yeah.
And so the function, I don't know if you already know what this function looks like. It basically just looks like
Parabola.
looks a lot like a parabola, but more squared off at the bottom.
Yeah.
Okay. And that's what the picture's telling us. Or that's what the math's telling us. Okay. X to the 1/3. And I'll probably skip the one after that because it's repetitive of what we've already done. So let's do x to the 1/3 really quick. So f of x is equal to x to the 1/3. What's our derivative?
1/3 of x to 5 negative 2/3.
Or in other words, it's 1 over 3x to the 2/3, right?
Yeah.
And then finally our double derivative. Bring down the minus 2/3, so it's going to be negative 2/9 x to the minus 5/3, right?
Yeah.
Subtracting 1, which is the same thing as, I don't know why I wrote that so big. This was 3x to the 2/3. This one is going to be negative 2 over 9x to the 5/3. Good? Okay, critical points.
0.
Just 0. To the left of 0, do we get positive or negative?
Positive.
Positive. To the right, we get
Positive.
positive. Okay, so that's our slope. Our slope is always increasing. Let's look at our concavity.
Negative. And then positive.
Our concavity is, first off, 0 is where it could potentially switch. So this could be an inflection point. Check to the left. Plug in a negative number, what do we get?
We get positive.
We get positive.
I didn't see
Oh, there's a
that.
negative.
Yeah, so
Alright.
positive. And if we plug in positive, we get a negative.
Alright.
So the concavity switches. It goes from concave up to concave down.
But increases all the way.
But it's always increasing. Okay, so let's, I don't know if you already know what this function looks like, but, so we want concave up, but increasing. Right? So that's going to be the right-hand side of the smiley face, but this one's going to be very stretched out smiley face. So it looks like this. And now we're concave down, but still increasing. Right? So it's going to look like that. Frowny face, but the half of a frowny face where it's increasing.
So 1/4 of the front face.
And so there's what x to the 1/3 looks like, kind of like a cubic flipped on side. Good? Okay. Well, maybe we should do this one so that everything isn't just centered at 0. So next one, x to the 4 minus 4x cubed, what is it, plus 10? Okay, so what is f prime of x?
4x cubed minus 12x squared.
And what is f double prime of x?
12x squared minus 4x.
Okay, this is equal to, let's just factor it really quick. I'm going to pull a 4x out of everything.
4x
X squared.
Wait, what?
Yes. Pull a 4x squared out of everything.
Oh, yeah.
Over here I'm left with an x minus 3. And now this one, pull the 12x out of everything. And I'm left with
X minus 6. Oh, thanks.
good?
Is that on purpose? From the author?
I assume so.
Maybe factor.
Oh, yeah.
Can double check that we wrote this right. X to the 4 minus 4x cubed plus 10. Okay, so we want to figure out where this function is. So this one is tracking slope, so our critical points. Let's look at our critical points. Where are our critical points? Where is the derivative 0 or undefined?
That's
0 and
0.
3.
0 and 3. And then, for concavity, where are our potential influx
0 and
points? 0 and 2. Right? And let's really quick check on each of these intervals. Our slope, if we plug in a number to the left of 0, what do we get?
A negative number.
A negative number. If we plug in a number between, plug in something like 1, what do we get?
Negative number.
Negative.
And if we plug in something bigger than 3,
Positive.
and then over here, plug in something to the left of 0, plug in something like 1.
Hold on. If you plug in something to the left of 0, don't you
Oh,
get
oops, that's not squared. Sorry. Yep, do that again.
Oh, yeah.
Thinking too quickly. That is not squared. So plug in something like negative 1,
You get a negative times a negative.
which is positive. Plug in something like 1,
Positive.
negative. Right? This one becomes negative, this one's positive. And then plug in something bigger than 2,
You get positive.
positive. So concave up, concave down, concave up. Okay, so now let's get a feel for what this graph must look like. I need to get a sense for the height at each of these points. So let's see, what is f of 0 equal to? 10. Let's find f of 3. Plug in 3 up here. 3 to the power 4 is?
72.
9 times 9 is?
81.
81. So 81 minus, what's 4 times 27?
4 times 27.
What's 12 times 9?
81.
What? 12 times 9. 9 times 9 is 81.
4, no.
4 times 1 of the
108.
3s times the 3 squared. 108. And then plus 10. What does that equal?
So fast.
Negative 17.
72.
What?
81 minus 108. You need 19 to get to 100, and then 8 more gets you to 27, plus 7 gives you the 17, and it's negative. Okay, so that's negative 17. The f of 0 here, is that going to be a local max or a local min or what?
Modified.
Neither. It just
Oh,
keeps
yeah.
decreasing there.
Yeah.
It's just that the slope is 0 there for a little bit. It's going to be an inflection point. Oh, really quick, let's get f of 2. When we plug in 2, what do we get?
16.
16 minus 32 is negative 16, plus 10 is negative 6. Okay, so now let's very roughly sketch this out. F of 0 is up here at, we'll pretend that this is 10 marks. 10. So negative 10 will be about right there. Negative 20 will be about right there. So negative 17 over here at 3. F of 3, negative 17, somewhere like right there. And then f of 2 is negative 6, somewhere like right here. Right? Okay. Now, from negative infinity to 0, our function is decreasing. And what's the concavity? Up. So it's the part of a smiley face that's decreasing. So something like this. With the derivative being 0 there, right? Kind of move that 10 out of the way. And then the concavity switches to concave down until we get to 2, and it's still decreasing. So we still have negative concavity. At 2, we switch to positive concavity, and we're still decreasing all the way to 3,
You're increasing.
decreasing till we get to 3.
Oh.
And then at 3, we start increasing again with positive concavity. And so very roughly, that is what that function looks like.
Crazy.
This one is a local min, and it's also the absolute min, if it asks you to find those.
How do we find out the limit?
It's the lowest of all your, if it has an absolute min or a local min, it has to occur at a critical point. So you only have to check your critical points. So these were our 2 critical points. If it had a max or a min, they had to occur at one of those points.
That would be min then.
It doesn't have an absolute max because we go up to infinity.
Is there?
That's a min, it's going to be an absolute min.
Is there a way of checking a function to see if it has an absolute limit? Besides checking a critical point.
No.
No.
I mean, there's probably other ways of doing it, but not with the tools you have available to you. Right now, the only way that you know how to find an absolute min is to check all the potential local mins. Basically, check all your critical points. Okay. Let's see. We'll just do one of those examples. Which one of these do you want to do? Top or bottom? Bottom? So we'll do the bottom one. That one is going to include some asymptotes now. Don't forget about your asymptotes. X squared plus 4 over 2x. Now I instantly know you have horizontal asymptotes where you're undefined.
0.
0. Or sorry, not horizontal, vertical asymptotes where you're undefined. So I know whatever this function looks like, it has a vertical asymptote at the y-axis. So I know that the y-axis here is a vertical asymptote. And you have an oblique asymptote, since your numerator is 1 power higher than your denominator.
At 2, right? Or at 1 half.
Well, it's going to be an oblique one. And so the way you do it is you have to calculate the division. So reminding you of stuff you already did, x squared plus 0x plus 4, and we're dividing that by 2x. 2x goes into x squared, 1/2 x times 1/2 x times 2x gives me x squared, right?
Yeah.
Bring down the plus 0x, subtract it, sorry, and then bring down the plus 0. Gives us 0 plus 0x
Which is 0.
plus 0. And then bring down our 4, and then plus our 4 is our remainder, 4 over 2x, whatever that is. So our oblique asymptote is a line 1/2 x plus 0. So we have,
Isn't it 1/2 x plus 4 over 2x?
no, your remainder in the limit as x goes to infinity, that goes away. And so your constant is a 0 here, and it happened to be 0. This could come out a number like 5. In that case, your oblique asymptote would be the line with y-intercept of 5 and the slope 1/2. So our oblique asymptote has a slope of 1/2 and a y-intercept of 0. So our oblique asymptote looks something like this. Okay, so there's our two asymptotes, just from looking at the picture so far. Now, let's fill in what we know from stuff we learned this chapter, rather than just testing points and plotting it. Right, that's what you had to do before, is just start testing a bunch of points, get a feel for it, see what's going on. Now we'll use what we learned from this chapter. So let's look at let's look at its derivative. What's the derivative of that?
2x.
No, it's the short.
Low D high.
Yeah, 2x.
Oh, that's what you're doing. I thought you were calculating the derivative of that.
No, I was actually going to do it.
Low times the derivative of the top,
This is 2x.
minus the top times the derivative of the bottom.
4. What?
The bottom times the derivative of the top, minus the top times the derivative of the bottom,
OD high, high D low. Oh, yeah, you're right.
all over the bottom squared.
And the bottom away we go.
There we go. Okay, so this is going to be equal to,
I did before there.
2 squared.
I squared that. What's 2 squared?
What?
What's x squared?
X squared is x squared.
And 2 squared is?
4. Oh, you squared them both.
I squared the bottom.
Oh, that's
Look.
right. Okay.
What is 6 squared equal to?
12. Or 16, 32.
36.
36.
36. Another way I could have written 6 is 2 times 3. If I square 2 times 3, I have to square both terms.
Yeah.
I can't just square one term. If I just squared one term, I'd get 4 times 3 would be 12. So this is equal to 2 squared times 3 squared, which is equal to 4 times 9 is 36. Didn't change our answer. So when you square it, you have to square every term.
Okay.
Okay. Anyways, this comes out to 2x times 2x is 4x squared minus 2x squared. You follow that? Plus 8. Or still minus 8, sorry. So negative 2x squared and negative 8.
Why is it negative 8?
Negative 4 times
Oh,
2.
okay.
Yeah. All over 4x squared. Or, in other words, f prime of x is equal to 2x squared minus 8 over 4x squared. Right? Factor a 2 out of the top and cancel out top and bottom, and we're left with x squared minus 4 over 2x squared.
Okay.
Factor that. That is the same thing as x minus 2 times x plus 2 all over 2x squared. Good?
Okay, yeah, we're
Alright, so there is our derivative. Now we need our second derivative for concavity. So f double prime of x. And so which of these will be the easiest to take the derivative of?
Probably the first one.
Probably take the derivative of this.
Yeah.
Will probably be the easiest. So we have the bottom
2x.
times the derivative of the top
2 is 2x.
plus the top
Which is x squared minus 4.
times the derivative of the bottom
4x.
all over the bottom
4x.
squared, right?
Yeah.
Okay, and this is going to be equal to 2x squared times 2x is going to be
4x cubed.
4x cubed plus, over here we're going to get 4x to the 4, or 4x cubed again,
Yeah.
Yep.
and then we have minus 16x. Did I do all that right? All over 4x to the 4, which is going to be equal to 4x cubed, and 4x cubed is 8x cubed minus 16x all over 4x to the 4. Cancel out a 4 with everything. Well, maybe pull an 8 out of these and 8x out of those first. So I have 8x times x squared minus 2. Did I do that right?
Yeah. Okay.
All over. And I'll rewrite this as 4x times x cubed. Right?
Yeah.
Now 4x cancels with the 8x, leaving 2 in the numerator. So this is going to be 2 times x squared minus 2 all over x cubed. Good? Okay. Let's erase this step since it's got in the way of our graph. But go from there. Okay, so what are our critical points? Where is our
0.
derivative 0 or undefined?
0, 2, and negative 2.
0, 2, negative 2. And if I plug in negative 3, what do I get? I get negative, negative, which is positive.
Is negative.
No, because the bottom's always positive.
Oh,
Right.
yeah.
Okay, plug in something like negative 1, I get negative, positive is negative. Plug in 1, I get negative, positive is
Negative.
negative. And I plug in 3, I get positive, positive is positive. Okay, so that was for our slope, and now for our concavity. Where is our concavity, 0 or undefined?
0.
0 is 1, where else?
Square root 2.
Where this is equal to 0, so where is
Oh, look.
x squared minus 2 equal to 0? Well, that's where x squared is equal to 2, or where x is equal to plus or minus the square root of 2. So, minus root 2 and plus root 2, right? And then checking the concavity, plug in a number more negative than there, so plug in something like negative 2. Positive, negative gives us
Negative.
negative. Plug in something between 0 and square root of 2, but still a negative number. So this will be negative. This will be positive minus something smaller than 2 minus 2 will be negative.
So you'll have positive.
So negative over negative will be positive. Plug in a positive number smaller than square root of 2. So this will be positive.
It'll be negative.
Positive minus that will be negative. And then plug in something like 2, and we're back to all positive.
Yep.
So concave down, concave up. So all three of those points are inflection points. And now let's really quick get the height of each of these points, and we're ready to go. So let's look at f at negative 2. We'll go left to right. What is the height of our function at negative 2? 4 plus 4 is 8. Divided by negative 4 is
Negative 2.
Negative 2.
negative 2. Let's look at f at
6.
negative square root of 2. So 2 plus 4 is 6. Divided by negative 2 square root of 2.
Is 3.
It's going to be negative square root of 2 over 3, right?
Yeah.
Did I do that right? Negative root 2 over 3. Which will be between a half and 1, somewhere in that range. Let's look at f of 0. What do I get if I plug in 0?
You get
Undefined. That's how we knew that we had this vertical asymptote. We made the denominator 0. And then f at square root of 2, what do we get? 6 over 2 square roots of 2, or in other words,
same thing as before.
oh, 3 over the square root of 2. And this other one was negative 3 over square root of 2, right? The square root was in the bottom.
Yeah.
Okay. And then finally, f at 2 gives us gives us 2. Okay. So, there we go. Negative 2. Over here at negative 2. We go down to
Negative 2.
over here at positive 2. we go right here. Our points of inflection happen at negative square root of 2, negative square root of 2, we're at negative 3 over the square root of 2. So that's going to be, how big would that be roughly? That's going to be smaller than 2, right? That's going to be like right here.
Oh, yeah.
Because the square root of 2 is less than 1.5. It's 1.4 something. So slightly bigger negative number. I think I'm thinking about that correctly. And then this will be slightly bigger like this. Not doing those very symmetric, am I? Because I made those jump up way more. Should have been a little bit more careful with my picture here. But I think we get the idea. Okay, so now, coming in from negative infinity to negative 2, I am increasing, and I'm concave down. Concave down, is that frowny face or smiley face?
Frowny.
Frowny face. So I'm coming in like a frowny face. And I stay like a frowny face all the way until I get to that point. That's my inflection point, is at the square root of 2. Right? And then there, I switch to the end of a smiley face. The decreasing end of a smiley face, because we're still decreasing, right?
Yeah.
So I was increasing up to that point, now I'm decreasing, and I don't know how to draw this very well. But running away towards that thing. Wait,
No.
how could that be concave up?
That's not.
It is.
No. That's a frowny face.
You drew it wrong.
If it's, what?
Want to go like that?
Let's see, what one are we on?
I have no idea.
What?
Can,
Sketch the graph. Okay, I have it roughly how the graph looks. Oh, no I don't. We have this asymptote right here that we completely ignored. So we're going to be running off towards this asymptote, like that.
In the vertical asymptote. Well, that's still not talking about.
Yeah, no.
What?
So, let's see. This is concave down. And then from here to here, let me see what they got for their second derivative. See if they wrote it out. So their derivative, f prime of x, they got x squared plus 4 over 2x. We did something really weird.
What?
Oh no, that was the initial one that we started out with. Oops, what did we have here?
Square root of the negative. Negative 4.
F prime of x, they have x squared minus 4 over 2x squared. That's what we got, right? For their second derivative, they just have 4 over x cubed.
That's not what we got.
4 over x cubed. Let me split this up and just think about it a different way. So this is x squared over 2x plus 4 over 2x, right? Take the derivative. This, first off, this is equal to just x over 2 plus 2 over x. Am I thinking about that right?
yes.
Cancel out an x, cancel out a 2. Okay, now
Yeah.
take the derivative of this. So now when we take the derivative, we're going to get 1/2 minus 2 over x squared. Take the derivative again, that's going to go away. We're going to get
Once you get it 1 over
2 over x cubed.
4.
Bring down the 2. That would be 4. 4 over x cubed. Is that what they got? Yeah. I have no clue what we did in making our mess, but we did something wrong. bottom times the derivative of the top minus the top times the derivative of the bottom.
Is it minus?
Yes.
Oops.
Okay, so there was an obvious mistake, and we erased a step. But let's see here. All of our x terms better cancel out. So we have 2x squared, we have 4x cubed, and we have negative 4x cubed. Okay, and then negative is plus 4.
So you have
Wait,
4x
oh.
over 4x,
4x, so 16. So we should have gotten 16 over 4x to the 4, right? Or 16x. And then cancel out 4x top and bottom, and you get 4 over x cubed. Okay. So we went crazy with inflection points. Our only inflection point was potentially at 0, right?
Well, 0 is the asymptote.
Right, and it's also our only potential inflection point, but it's not an inflection point because there's no tangent line there.
Yeah, you can't. Yeah, right. Right.
But our concavity to the left now is going to be negative, and to the right is going to be positive. So yes, this whole thing is concave up. All those square roots that we were calculating, there was no point, and this whole thing is concave down, concave up. Wow, we made a mess of that, all due to that one time. Thanks for the help, guys. Okay,
Good the teacher.
yeah. We won't bother with this one. Similar idea. I think you know how to do these from here on out. We won't do other examples, but jump straight to the physics one. Intuitively, what does the derivative give you if this is a position function? So here is a position function. This is a one-dimensional position function telling us where the position of a particle is over time.
Okay.
Right? So my position over time, if it was tracking me, I might go forward, stop, go backwards, go forward again. And this S of t is saying how far I moved from where I started after some amount of time t, but just moving back and forth. So now, the derivative of our position, we already talked about, gives us our velocity.
Yeah, I remember this.
And so the velocity then of this is just going to be, calculate the derivative,
16
minus 28t plus 22, right?
Okay.
And then, concavity is the same thing as our acceleration,
Oh, that makes sense.
which is the derivative of our velocity. So our acceleration function now, because
Oh, yeah. Right.
positive acceleration means you're increasing your velocity. And your velocity is just the change in your position. And so our acceleration function here would just be 12t minus 28, whatever that is.
Yeah.
That's an excellent T.
That's nice.
What's a t? Oh. Okay. Good?
Yeah.
And they did it wherever your function is increasing or decreasing is where your velocity is increasing or decreasing. And where your concave up or concave down is where your acceleration is increasing or decreasing. And same thing. So if I ask you to find where is the velocity increasing, that's the same as where the slope is increasing in what we've already been doing. And if I ask you to find where is the acceleration decreasing, that's equivalent to saying where is it concave down, and vice versa. Don't want to spend any more time with that because I want to get to all these examples. You good with that?
Yeah.
Okay, so you're going to be told over and over again, graph the function using the fact that you know how it's increasing and decreasing and whether or not it's concave up or concave down. Now this next section is much, much more interesting, and we finally get to some fun stuff, what I think is fun stuff.
There is that.
Yep. And here, you're going to start getting a sense for why it's so useful to know these local maxes and these local mins. So our first problem is we've got a warehouse full of little cardboard pieces that are 1 foot by 1 foot. We decide that we're going to make a bunch of boxes out of those pieces of cardboard to put stuff in. With me so far? We want to maximize the volume of those boxes. So the question is, if I've got this 1 foot by 1 foot cardboard piece of cardboard, what is the biggest box I could possibly make out of that? We're not going to put a lid on the box. So the way we're going to make our box is we're going to cut out these corners and then fold up the edges. And we want to create a box that can hold as much material as possible. We want to maximize the volume of our box, right? Notice that if we don't cut anything, how much can our box hold? It can't hold anything. Imagine it's a container and we want to hold something like water. If I take my cardboard box, piece of cardboard, and I don't fold up the edges at all, it can't hold anything. It's completely flat. You with me? On the other hand, what's the biggest I could cut out of the corner? 6 inches. If I cut out 6 inches from each corner, I've cut out my entire box. So the question is, how much should I cut here to maximize the volume of my box? If I don't cut anything, my box can't hold anything. If I go all the way to 6 inches, well, now I've got nothing. So whatever my answer is, it has to be between 0 and 6 inches.
3.
Is it going to be 3? We just going to guess? We got millions of these boxes that we got to cut. If you're off by 1 cubic inch from what you could have gotten across millions, that's millions of cubic inches you just lost in materials. Or in storage capacity, or whatever it is you care about. So we're very interested in, here's a very real world example of where we're very interested in, how much should we cut? So that they can store as much as possible. And so we're going to figure that out. So first off, we need to find the volume of the box as a function of x. What is the volume of a box? Length times width times height.
Cubed.
It's just length times width times height, right? What is the length of the box?
12 inches.
Well, I'm going to fold those up.
Yeah,
So once I fold those up, what am I left with?
Whatever it is.
12 minus how much did I take off? Huh?
Subtract 2x.
So there you go. Subtract 2x. There's my length. That's how wide this box is once I cut out x and fold it up. What's my width?
the same
Same.
Same thing. What's my height of my box?
x.
X, however high the lip is that we're folding up. So here is my volume as a function of x. If we were to graph out this function, whatever it would look like, it's going to be 0 here at 0. If we cut nothing, the volume's 0, right?
Yeah.
And then at 6, it's obviously 0 as well, right? So our function is going to look something like this. We want to know where it's at its max. Or in other words, we're calculating a local max of this function. What is a property the function has at its max? What's the derivative there? 0. So we want to find the x that makes the derivative of the volume 0. So let's calculate the derivative of the volume with respect to x.
But you have to use chain rule because it's
2
right.
times
Yeah, maybe let's multiply this out and treat it as just a big polynomial. So 12 times 12 is 144 times the x. We have 12 times negative 2x, and negative 2x times 12. So 12 times negative 2x is negative 24x, and negative 2x times 12 is negative 24x, so that's negative 48x. Then that x is negative 48x squared. And then finally, negative 2x times negative 2x is
Plus 4x.
positive 4x squared times the x is positive 4x cubed. All right, a little bit easier to work with, right? Okay, now let's take the derivative. Let's start with this term. I want to write my highest power term first. So what's the derivative of this?
12x squared.
12x.
12x squared,
96x.
96,
144.
plus 144. So there's our derivative. Let's factor 12 out of everything. So that's going to be 12 times, we have x squared minus
8.
8.
12.
Minus
Okay.
x.
Now we want to factor that. So that's going to be, I'm looking for the x. 2 x's, multiplied together give me 12, added together give me negative 8.
6
6 and 2.
Negative 6 and negative 2, but yeah, you have to write it. Okay, and so now, that is our function. We're looking for the local max. So where is our derivative equal to 0?
2 and 6.
2 and 6. So if we were to graph out the function of the sink, it would actually look more like this. Over here at 6, it had a slope of 0, and over here at 2, it had a slope of 0. And so what is our local max?
2.
At 2. So that's telling us cut out 2 inches, and that maximizes your volume. So what is our max volume going to be? What is the volume of our box going to be if we cut out 2 inches? It's going to be 8 times 8 times 2. So 128 cubic inches is the biggest box you can possibly make using that material. Make sense? Okay. Similar problem. Here we are, and we are some sort of a juice manufacturing company, and we've decided that we want to sell 1 liter bottles of our juice. So we're going to have them in cylinder containers. We know that we want our cylinder containers to hold exactly 1 liter, or in other words, 1,000 cubic centimeters. The question is, what should be the dimensions on our container to minimize surface area? Because if I'm making this like an aluminum soda can, the bigger the surface area is of the can, the more aluminum I have to use. I want to use as little materials as possible on this can containing our juice. So I want to minimize the surface area of it. I know I want it to hold 1 liter. Now, what dimensions should I give my can to use as little aluminum as possible to minimize the surface area? You understand the problem? Okay, so how can we minimize the surface area of the sink? We know the volume we want to be that. First off, what is the volume of a cylinder equal to? What's our formula?
Is it pi r squared times h? Or?
It's the area of the base times the height. So yes, area of the base is pi r squared times the height. So this is the volume of our container. We know we want our volume to be exactly 1,000 cubic centimeters. We're trying to come up with the dimensions for the radius and the height that minimize the surface area. Right?
Yep.
Okay. So we need an equation for the surface area here.
Is this with the lid or?
Yeah, this one is going to have a lid. So it's a container. It contains our juice. Think about it like a soda container. Minimize the surface area. We want to use as little aluminum or whatever we're using out to make our can as possible. So minimizing the surface area. So what is the area of that cylinder?
Of the cylinder?
What is
Or
it?
the surface area?
The surface area of the cylinder.
It's,
You need the circle at the top.
yeah, 2 pi r squared.
So pi r squared is the circle at the top.
Isn't it 4?
2 of them to give us the circle at the bottom.
Uh-huh.
And now we need the area of the piece that wraps around.
Which would be circumference times height.
Yeah, so imagine I took this thing, took the piece that wraps around, and I flattened it out right here. So if I flattened it out like this, how big would the top of this be? It would be the same big as the circumference of this sink if I flattened it out. And the circumference is 2 pi r, right? And then the height here would be whatever the height was there, h. So it's going to be plus 2 pi r h. Follow the algebra there? Okay. So here is the formula for the area, the surface area of our can. We are trying to find we're trying to minimize the surface area where our can is going to have a volume of exactly 1,000 centimeters, 1,000 cubic centimeters, or 1 liter.
Can we factor out a 2 pi r from that?
Sure, if you want.
I'm just wondering if we could simplify it more.
So, well, we'll leave it like that for now. But using our given information, what do I know? I know that whatever my radius and my height are, I know that pi times my radius squared times my height has to equal
1,000.
1,000. Because I already know that I want my container to hold exactly 1 liter. I can't take my derivative of this function yet because I have 2 variables. I have an r and I have an h. Do I take the derivative with respect to r or the derivative with respect to h? We don't know what to do. So we have to use our given information to either rewrite my r in terms of an h or rewrite my h in terms of an r. In this case, it's easier to replace my h with an r. using this information. So using this information, that gives me that h is equal to 1,000 divided by pi r squared. You follow that? Now substitute that in up here. And so my area, whatever it is going to be 2 pi r squared plus 2 pi r times h. Good? Now let's simplify that. So my area is going to be equal to 2 pi r squared plus the pi is going to cancel out top and bottom. This r is going to cancel out with one of those r's. And so we're going to get 2,000 over r. You with me?
Yeah.
And now we can take the derivative with respect to r. And so the derivative of a with respect to r.
2 pi.
And if we were to graph this out, I mean, I don't know what this thing would look like, but whatever it would look like, if we plug in a really small number for r, we can't really plug in 0 for r, can we?
No.
Why can't we plug in 0 for r? If I make the radius 0 and my volume has to be 1,000, what does my height have to be? Infinite, right? So this thing shoots up to infinity and it comes down and goes something like that, whatever it does. And we're looking for the minimum here. What r gets us the minimum surface area?
The local mean.
Yeah, so we're looking for the local min. And that's going to be wherever the derivative is equal to 0 is where that local min is going to occur. Is the point. I told you, these application problems, we are very interested over and over again in finding local mins and local maxes.
That's cool.
Use it all the time. So this is going to be equal to, we're doing the derivative with respect to r, so bring the 2 down, gives me 4 pi r plus, this is the same thing as r to the minus 1, so bring down the minus 1, gives me a negative here. 2, 0, 0, subtracting 1 would be minus 2, or in other words, r squared like that. Follow the algebra there?
Yeah.
Yeah.
Because the r there, that's the same as r to the minus 1, so bring down the minus 1 and make it minus 2.
Okay.
Now, where is this equal to 0? So I want to know where is 4 pi r minus 2,000 over r squared equal to 0. That's going to happen when this equals that. Just move that to the other side. So that is going to be when 4 pi r is equal to 2,000 over r squared.
You divide.
Multiply this side by r squared and divide this side by 4 pi, and I get r cubed is equal, 2,000 divided by 4 is 500, and then divided by pi is just over pi.
Okay.
Okay? And so that gives me that r is equal to the cubed root of 500 over pi. And whatever that number comes out to is going to be, I think I left my calculator. But whatever that number comes out to, it's going to be in terms of centimeters. Yeah, 500 over pi cubed root, or to the 1/3.
It'll be about 5.4 kin.
So r will be about, you said 5.14?
5.4 kin.
5.42 centimeters. And what will our height be? Well, let's calculate our height plugging in r here. So our height is equal to 1,000 over pi times our radius squared. So pi times
5.4 kin.
500 over pi to the
1/3.
to the 1/3 but squared, so to the 2/3.
Oh, yeah.
You with me?
Yeah.
Okay, so this is going to be equal to, let's do some algebra here. This, I'm going to flip it to the top and make it minus 2/3. So we have 1,000 times pi to the, well, it's not going to be negative 2/3. I don't know. Are you guys following that algebra if I just put the 2/3 up there? The bottom of the bottom goes to the top.
Okay.
over, there's this pi here, times 500 to the 2/3. You with me? So pi to the 2/3, since it's in the denominator of the denominator, that's the same as the top.
Right.
And then the 500 to the 2/3 still right there. So that's going to be equal to, let me rewrite this in a very telling way. 1,000 is the same thing as 2 times 500 to the 3/3. And then we're going to have times pi to the 2/3 all over 500 to the 1/3 times pi to the 3/3.
2/3.
3/3.
I'm saying 500.
Oh, thank you. You're saying that to 2.
Yeah.
Good. Now 3/3. Remember, if your exponent's in the bottom, if you bring it to the top, it just makes it negative. So add exponent. So this is going to be 2 times 500 to the 1/3 over pi. If I move that to the bottom, it becomes negative. Pi to the 1/3. You see that?
Yeah.
Which is the same thing as, we'll put it up here, this whole thing is just r. That's just the cubed root of 500 over pi. So it's 2r. So your height is exactly double your radius.
Okay.
What?
Or you could have plugged it into your calculator and you would have gotten that your height is approximately, just using this formula, you would have got that your height is approximately 10.84, depending on how the decimal places come out, maybe an 8.5 there. Centimeters. And that's the exact dimensions you should use if you want to minimize the amount of material that you use to construct this container to hold exactly 1 liter in it. Good? All right, next one. Next one, we have a rectangle inscribed inside of a semicircle. We are trying to find the rectangle that has the largest area, but it has to stay inside of the semicircle. So a potential rectangle could look like this. I can make it tall and skinnier. Another potential rectangle could have looked like this, wider but shorter. Question is, what point should I use to construct my rectangle so that we maximize the area of the rectangle and keep it inscribed inside that semicircle?
Yeah.
You understand the problem?
Yes.
Okay, so first off, what is the area? Oh, and it was given that the circle has a radius of 2, I can't remember meters or whatever, but 2.
Okay.
So we know the radius of our circle.
Okay.
Trying to find the max area of a rectangle we can fit in half a circle.
Okay.
With radius 2. Okay, so what is the area?
Length, width.
So length times the width.
It's the length times the width. So what is the length here? If we call x how far we go out,
2x.
it's going to be 2x times the height. What's that height going to be?
Y.
Let's scribble this with a triangle over here. If I give you a triangle, I tell you that's 2 and I tell you that's x, what's this? If we know it's a right triangle.
It's
Let's just call it y for a second. And then we'll find y in terms of x.
z squared minus x squared.
Well, that's a 2, but perfect. Almost got it. So we know that x squared plus y squared equals 2 squared, right? We're solving for y. So y squared is going to be 4 minus x squared. So y is going to be plus or minus the square root of 4 minus x squared, right?
Yep.
And so the height of this thing is going to be the square root of 4 minus x squared. Positive because obviously we don't have a negative height. Good with that? Okay, so there is our area. Now, we are trying to find the x that maximizes our area. So our area as a function of x, obviously I don't want x to equal 2. If x equals 2, so if I use this point to construct my rectangle only has length and no height. So the area is 0. So if you plug in 2 for x, you get 0 area. Furthermore, well, if I decide to use my rectangle and just make it go straight up and down to this point, it again has no area when I made my height 2. So if my x is 0 and my height is 2, then I get no area. And if my width is 2, or my x is 2, and my height is 0, then I get no area. Which is what the 2 zeros here are talking about. See that from the math? So whatever this function, area function looks like, if we were to graph it, it'd look something like that. It's going to have a max somewhere where the derivative is 0. Our job is to find that number that corresponds to a 0 derivative. What x gives it its max area? So, we have no space here. What is the derivative of our area with respect to x? Equal to the derivative of the first multiplied by a second plus the derivative of the second.
Wait.
So the derivative of the second, remember square root is the same thing as to the 1/2.
Yeah.
So bring down the 1/2. Now it's to the, if I bring down the 1/2, now it's going to be to negative 1/2, which is the same as sticking in the denominator. So 1 over the square root of 4 minus x squared. And then chain rule times the derivative of the inside is negative 2x. You follow that?
Isn't it minus, not plus?
No, it's plus.
We bring down the positive 1/2.
I
And
mean
then-
You minus it if you're dividing.
For the chain rule is a negative 2x. Oh, you're saying right here?
Yeah.
No. That's for the quotient rule.
Right, okay.
Okay, I see what you were thinking.
Oh.
Alright, so simplifying now. 2 times the square root of 4 minus x squared still. But here, this 2 is going to cancel out with that 2. And so we're going to get minus x over 4 minus x squared under the radical. With me? And now, we want to know where this thing is equal to 0. Where our derivative is equal to 0. You with me? So move this to the other side. So that's going to be where 2 times the square root of 4 minus x squared is equal to x over the square root of 4 minus x squared. You with me? Times both sides by the square root of 4 minus x squared. So we're going to get 2, move this way some so I can do more than that on one line. 2 times 4 minus x squared equals x. Multiplying both sides by the square root of 4 minus x squared. It's going to cancel out top and bottom there, and then that's going to make it not square rooted anymore. Okay. So this is going to give me that we have 8 minus 2x squared equal to x.
Take an x out. Or no.
Why do I get the feeling I messed something up? Length times height, that's good. The derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. We have times 2x up here.
Wow.
This is worth writing out again to make sure it's super clear. Okay, yeah, something felt weird. Do it again. The first times the derivative of the second, or sorry, the derivative of the first multiplied by a second. So the derivative of that multiplied by that gives me 2 times the square root of 4 minus x squared. Now, I'm going to add it to the first times the derivative of the second. Now times the derivative of the second. And the derivative of the second is bring the 1/2 down. Times, that leads me to the minus 1/2. So that's going to do the square root in the bottom. And then chain rule gives me a negative 2x.
Where's the negative place?
What's the square root of 4 minus x squared?
What's
But, okay, let me rewrite just this term now. That term is 4 minus x squared to 1/2. Let's do its derivative. bring down the 1/2. We still have the 4 minus x squared, but now it's to the minus 1/2, which is the same as putting it in the denominator. And then chain rule times the derivative of the inside is minus 2x. So that is exactly what I have written here. Okay, now we want to know where this is equal to 0. Let's simplify this a little bit. Bring my negative sign out here. You okay with that? And then this 2 can cancel out with that 2. So we'll cancel out that with that. So this is going to be equal to 2 times the square root of 4 minus x squared minus 2x all over 2x squared all over 4 minus x squared under the radical. Did I do all that right? Negative 2x times x is negative 2x squared, and that's all we have in our denominator now. And I want to know where this is equal to 0, so I'm just going to move this to the other side. So I want 2x squared over the square root of 4 minus x squared. I want to know where this is equal to 2 square roots of 4 minus x squared. Just moving this to the other side. Multiply both sides by the square root of 4 minus x squared. So over here, those will cancel out, and I'll be left with 2x squared is equal to, over here, we'll have 2 times 4 minus x squared. Like that. With me? Which is equal to, simplify the right-hand side here, we'll have 8 minus 2x squared. So 2x squared equals 8 minus 2x squared. Bring that 2x squared over here, and so we're getting 4x squared is equal to 8, which gives me that x squared is equal to 2, which gives me that x is equal to plus or minus the square root of 2.
Yep.
And what is our answer going to be? What should our x be?
Not positive square root.
Positive square root of 2, not negative. So go over square root of 2 and go up however much that makes you go up, and that rectangle will maximize your area.
What will the height be? Right.
The height, so the height is right here. So the height would be 4 minus square root of 2 squared is
So it'd be 2. So it'd be square root of 2.
square root of 2. So your height would be the same.
Oh. Oh, so it's a 45-degree angle.
So 45-degree angle maximizes the area.
That makes sense. That makes
Yeah,
sense.
pretty intuitive.
Okay.
Probably could have guessed it.
Probably.
Okay. Good?
Yeah.
One more example from physics, and then we're done. We're going to derive what's called Snell's law. Okay. Let me give you intuition for what the problem is. We are looking down, bird's eye view, at 2 swimming pools here. This swimming pool is full of water. This swimming pool is full of mud. Your task is you start at point A, and you're trying to get to point B as fast as you can, and you have to go through the pools. The question is, what path do you take? It's easier to go through water than it is through mud, right?
Yeah.
So what should we do? Should we just go all the way through water like this to that point and then go straight down through the mud and go through as little mud as we can?
You want to
Right?
Yeah, right.
The question is, what path should we take to minimize how long it takes us to get from point A to point B?
Uh-huh.
What's the exact point P we should go through? Where should we transition from our mud, from the water to the mud?
Depends how slow you are.
Right, it depends on what the materials are. So we're going to calculate for any materials in general. I'm just giving you intuition for the problem. And so it could be, should we spend more time in the water to cut down on our time in the mud? What's the exact amount of time we should spend in the water? What should be the point that we aim for? So here I am, I'm lining up, I'm wondering, what point should I aim for? And I'm going to go straight to that point before I get into the mud to minimize my time and do this as fast as possible.
Right.
Now, that gives you intuition for the problem. Why is this called Snell's law? What the actual problem has to do with is light. It turns out the path that light takes is always a path that minimizes the time it takes to go from point A to point B. And so you notice that when light goes, light travels at different speeds through different mediums. It travels through air faster than it travels through water. And so, when you look at light going through your glass full of water, it bends the light and makes things appear different than they actually are. It bends the light. Why does it bend the light? This exact reason right here. Light is minimizing the time. It goes through the air at one rate and the water at another rate. And it will always go through it. It will always bend in such a way that it minimizes the time to get through those 2 points. And how does light just instantly know what point that is?
No idea.
It just does the calculation real fast. Okay. So that's the problem, is what will that point be? And from the point you can figure out what the angles would be, right? If you knew the point. Okay, so that's what we're trying to do. We're trying to minimize the time. So we're going to assume that whatever this liquid, this medium is, light moves through it at a speed of c1. And whatever this medium is, light moves through it at a speed of c2. If it's hard for you to think about the light, think about as you go through the pool. You travel through this pool at a speed of c1 and this pool at a speed of c2. We're trying to find the point P here that you should aim at to minimize your time. You with me?
Yeah.
Okay.
Now we're given A and we're given B. That's the width of each of the mediums. And we know D, the distance from point A to point B along here. So that's A, B, and D. They're this distance, and this distance. You with me?
Good.
We're trying to find X here. We're trying to find where we should put this point P, or in other words, find this X that minimizes our time.
Yeah.
With me?
Yes.
Now you've probably heard 1,000 times throughout your education, rate times time equals distance.
Yep.
Right?
Yeah.
If I'm going 100 miles per hour and I do that for 5 hours, how far do I go? 500 miles. If you want to get your time, you do your distance divided by your rate. If I went 300 miles in 6 hours, what was my speed? 50 miles per hour. Oh, oops, I did that wrong. If I'm trying to go 300 miles, and I know I'm going to drive at a rate of 50 miles per hour, how long will it take me to get there? 6 hours.
6 hours.
So time is distance divided by rate. Time is what we're interested in. So what is the time that it takes to go along this path? So your time to go along this path is going to be
C1 plus C2. Ah, yeah.
the distance from A to P, whatever that is,
Yep.
divided by your speed that you go through this first medium, which we called C1,
Yeah, right.
plus going from P to B, whatever that segment is, divided by C2. You with me so far?
Yeah, yeah.
Who's gonna be the fastest?
Well, no, this is just your time in general.
That's the total time. Yeah.
We don't know where this P shows up. This P could be right here, this P could be right here. We're trying to figure out where should we put the P to minimize your time. So that's what we're going to be minimizing.
Okay.
Okay. So now let's write AP in terms of all our variables here.
A squared plus.
Because ultimately we want this to just be a function in terms of X. X is how far in I should put that point P to minimize the time.
No A.
Little a is going to be a constant, little b is going to be a constant, little d is going to be a constant. They're not variables. We know how thick this medium is. We know how thick this medium is. And we know how far b over b is.
So it's
So x is our only variable here.
A squared plus X squared.
So yeah, what's the distance from A to P? What is that distance?
A squared plus X squared.
Under the radical.
Yeah.
A squared plus x squared is that distance. Okay, now looking at this one, what's this distance?
Likewise.
Oh. It's, it'll be,
So d is this total distance. Maybe put d down here.
please do.
So this is d. So what is this distance?
It's
D
D
minus
minus
X.
X.
D minus x.
So it'll be,
And what's our height here?
B.
Just b. So this is,
D minus X
minus
squared plus B squared. Or under
Yeah.
the-
so b squared plus d minus x all squared.
And back under the radical.
Under the radical, yeah. Good? So now our total time, plugging in our variables, our total time is
Well,
the square root of
A squared plus X squared.
a squared plus x squared
Over C1. B squared plus DX. D minus X squared.
So there's our t. We are trying to minimize t. We're trying to find a local min of the time t. So we need to figure out what is, I'll write down here, what is the derivative of time with respect to x equal now?
Is the speed a constant?
Yes. It's how fast you can move through the water and how fast you can move through the mud. And we're going to assume you go with a constant speed. Or it's how fast light moves through air and how fast light moves through water. And light doesn't change speeds as it moves through the air or through the water. Good?
Yeah.
Okay. So we're looking for the derivative of this with respect to x. So what is it? Let's scribble this term out to the side. That's the same as 1 over c1 times a squared plus x squared to the 1/2, right? What's the derivative of this with respect to x?
It's going to be 1/2 times.
Bring down the 1/2, so we bring down the 1/2, put it there. This becomes a minus 1/2, and then chain roll, so times,
The x is
2a plus, or just
What?
2x.
it's 2x.
2x.
Yeah.
the derivative of the inside is just 2x.
Yeah.
What's the derivative of a constant?
It's
0.
0. What's the derivative of x squared with respect to x?
2x.
2x.
Okay.
Okay, so just writing that out now,
Wait,
notice
what
that
about-
the 2 cancels with the 2 there.
Wait, what about 1 over c?
That's just a constant.
Meaning because it's 0. Or,
Okay.
yeah.
Okay. So we are just going to get, this 2 is going to cancel out with that 2. So my numerator only has x, and it's x over c1 times the square root of a squared plus x squared. You follow my algebra? Okay, let's look at the derivative now of this term. So looking at this term, let me rewrite it out for you again. So we're looking at 1 over c2 times b squared plus d minus x squared to the 1/2.
You
Okay.
got 1/2 down.
So bring the 1/2 down.
You got 1.
That becomes a minus 1/2. Now we need to multiply it by the derivative of the inside. What's the derivative of b squared?
It's 0.
0. B is just a constant.
Oh, that's
So now we just need to find the derivative of d minus x squared.
Which is
So let's really quick just do that to the side. We're looking at d minus x all squared. What's its derivative?
it's going to be 2x.
Bring down the 2. Makes that a 1.
Yeah.
And then multiply by the derivative of the inside.
2x.
Negative 1.
What?
Bring down the 2.
Oh.
Makes it a 1. And multiply by the derivative of the inside.
The d
What's the
turns to
derivative
0.
of d?
0.
What's the derivative of negative x?
Oh, I see it.
Okay. Don't be too quick to assume you know the derivative of something.
Yeah.
So that was the derivative of the inside of this. So multiply the whole thing by that. So times 2 times d minus x times negative 1. With me? So that is going to be equal to, this whole thing is going to be negative because of the negative 1, so I'm just going to put the minus there. Good? And this 2 is going to cancel out with that 2. So we're going to be left with, in our numerator, we have d minus x all over this whole thing with the c2. c2 times the square root of b squared plus d minus x squared. Did I do all that right?
I hope so.
Yeah.
Okay. So now we want to know where this is equal to 0. Where is a derivative equal to 0? So move this term to the other side, and it's going to happen when x over c1 times the square root of a squared plus x squared is equal to d minus x all over c2 times the square root of b squared plus d minus x squared. You with me? Why did it drop down there? Okay. Now that's kind of a mess, right?
Yes.
But let's notice something. Notice, without the c1 here, what is x over a squared plus x squared? That's x over a squared plus x squared.
It's,
Right? That is exactly the sine of theta 1.
Yeah.
What's the sine of theta 1? It's the opposite over the hypotenuse.
Yeah.
It's this over that. That's the sine of this angle.
Oh. Okay.
You with me?
Yes.
So, besides the C1, that piece is just the same thing as sine of theta 1
Times one.
over C1.
Yeah. Yes.
Because x over that is just sine of theta 1, and then we still have C1 in the denominator.
Yes.
You see it?
Yep.
Sine of theta 1, sine of this angle is just this over that.
Okay.
Or did you have a question? Okay. What's the sine of theta 2?
B.
Oh. Sorry. I wrote that in the wrong place. Our angle of inclination for this.
It would be
It's on the
on the other
opposite
side, wouldn't it?
On the other side.
PB up.
BP. Yeah, BP. Wait, isn't it?
PB up.
No. I'm not sure. Can't remember.
Our angle of inclination
Can't remember what it was.
because at d minus x it's just right here.
Yeah.
Done. I don't know why I blanked out so bad. It would have been the same as this piece of it. So what happens when you draw your picture so that your angles are too close? It's the same, right? Here's the angle of inclination here, and then obviously that's the same corresponding angle.
Okay.
Okay. It's good that you know Snell's law ahead of time so you know where you're supposed to go. And you can see what the problem is.
Yeah.
Okay, what's the sine of theta 2 going to be? It's going to be this over that,
Yeah.
right? Redrawing out this triangle. Imagine I took this triangle and flipped it right here. So here's theta 2. What is sine of theta? It gives us this side, which we typically call y, over this side, r.
Yeah.
Flip it over and put it back right here. There's our y, and here's our r.
So
D minus X
it'd
over
be
that.
sine of theta.
Oh.
So-
C2.
So yeah.
Right. Sine of theta 2 over c2. And that is called Snell's law.
Yep.
So it will go in such a way, these angles will be such that this quantity will always equal this quantity.
Yeah.
That's called Snell's law. I don't know if you've used that in physics yet, but you eventually will.
No, we just tried to use it in real life.
Well, we're not getting any concrete numbers because we didn't have any concrete numbers up here to work with.
Going back to the original problem with the swimming pools, there's also, I've heard of like the Vickrey-Chrome curve being the most optimal path.
That is through a medium that is consistently changing. And so you are thinking of a curve, I'm gonna do awful, but looks something like this.
Yeah.
And so what that curve is minimizing is, imagine that I wanted to have a ball roll down a hill. And I could design a ramp a bunch of different ways, but it starts out this high, it's gonna end up this low.
Oh, yeah.
I could have my ramp go like that, I could have it go like that. Obviously a ramp like this would be very dumb. But what is the optimal curve I should have so that the ball gets from point A to point B as quickly as possible? And it is a similar type problem to what we're doing.
Okay.
Ours is a very simple version, we're just finding one middle point. This, we're getting to a principle called the principle of least action in classical mechanics. But
How would you derive that curve? How would you go about deriving it?
not trivially. Not nearly as simple as this.
Okay.
You are minimizing, you're doing a sum of infinite minimizations. And so you're minimizing along the curve as you go, minimizing something called an action. There's probably a simpler way for this special case, but that's the general way.
Yeah.
And it's not something I can just, oh, here you go. It's a derivation in and of itself, and you would have to be comfortable with
A lot more than you are.
a lot of calculus.
Yeah. Oh, that's sweet.
you'd have to be comfortable with integrals for sure.
Yeah.
Because yeah, it's integrating
Integrating
the Lagrangian, which is the kinetic energy minus the potential energy. Doesn't matter. We're not in physics. There is a way to do it. It's not trivial, it's not easy, but yes, it's a very similar in idea to exactly what's going on here.
Yeah, I thought I recognized it. That makes sense.
Yes, it was the problem, if I'm not mistaken, that, oh no, I forgot his name. I'll script the history if I try to say it now. There's some history to that problem, some fun history to that problem, but without the names right, I'll lie to you, so I won't tell you the history, but sorry. Okay, but that's it for today. Lots of material, 3 sections worth. But outside of this homework section, I think the other 2 sections will be pretty easy. Where is the curve increasing or decreasing? These types of problems, unfortunately, there is no trick to. As you saw, every single problem had its own trick, its own way of solving it. You just have to think about the problem until you get it, understand it, and solve it. And
That's right, because it's fun.
That's what makes it fun, yeah.
yeah, that is what makes it fun. So these problems are much more fun. I like these types of problems.
Yeah. Sweet.
Any questions on anything? All right.
Yeah, thank you.
Next week we finish up the chapter and finish up the semester.